So far, we have defined the theory of optimization problems with the various definitions and conditions to find the local optimum. We've also talked about specific problem classes. Now let's look at how we can use the specific syntax to use the optimization toolbox in MATLAB. We'll see that it's very similar to the syntax that we use for the iterative solver functions in MATLAB. So here you'll see that you'll give the solver form and we'll specify the given input. Regardless of our solver, they all have the same format. So we can specify it input by input, or we can also specify a problem struct. So problem struct would be nice, cleaner code, so we don't have to give so many input arguments. But let's first look at what the outputs are. We'll see that your first output is x, which is the minimum value found, the vector corresponding to the minimum. Fval is going to be the value of our objective function at x, which is going to be the minimum of the function. The exit flag, again, will tell us the condition of the solver, where 1 means that it converged. We can also look at out, which will be the structure containing the output information, such as the number of iterations and how long it took to converge. Lam will return the Lagrange multipliers at x if we want to check the dual feasible condition. We can also return the gradient and Hessian of the objective function used. Okay, so what about the inputs? So the first F would be a function handle or a vector for a linear program defining our objective function and the gradient if we want to specify the gradient. We would have the second output of our function handle be the gradient function, just as we saw with the Jacobian in the prior example. So again, passing function handles are very important when using the optimization toolbox. X0 is going to be our vectors defining the initial guess. A and B are going to be the right-hand side defining our linear inequality constraints. A equal and B equal are going to be the right-hand side defining our linear equality constraints. Remember, they have the specified form that AX is less than or equal to B. LB and UB define our bounding box constraints. NLCon is going to be our nonlinear constraints. And we want to specify their Jacobians. We need to also have the second output of the function handle be the Jacobian matrix. Opt will be our optimization options struct, so this can specify our convergence criteria as well as the algorithm to use. If we turn display on, it will output the iteration count as well as the residual at every iteration, which can be very good for debugging. Okay. Or we can use problem, which will be a structure containing all of the above information. So now let's look at this problem structure in more detail, since this would be the nicer way to call the code. So instead of specifying so many different inputs to the call to the optimizers, we can store the inputs in a problem structure. So these are the corresponding fields. We can have problem.objective, problem.x1, problem.a inequal, equal L bound, and these are going to be the same as seen on the prior slide. Okay, and this can be very helpful in interacting with the optimization GUI, which we're going to talk about later. All right, so how can we use this option struct? In particular, what are the corresponding fields that we want to turn on and utilize? So each optimization solver has tunable options that can be specified with the option struct. In particular, we can use the opt-in set and then solver to return options available for particular solvers along with default values. Okay, so this gives us fine-grained control all over our solver. So we can specify the objective and constraint functions. We can specify the maximum iterations, the convergence tolerances, as well as if we want to supply the gradient and Hessian analytically or use finite difference for their computations. Since we'll be solving linear systems within the optimization package, we can also specify preconditioning and scaling. We'll see, especially when we're talking about the parallel computing toolbox, that we can turn parallelization to be on, which is ideally what you would like to do. So now let's look at the various MATLAB functions for the types of optimization problems that we defined. We've seen that for linear programming, in MATLAB we can use the linprog function. If we have a binary integer program, we can use bintprog. If you have discrete integer program, you can use intlinprog function. For a quadratic program, which has a quadratic objective, you can use the quadprog function. If we have no constraints, fmin search and fmin unconstrained are viable alternatives. And for constrained optimization with general nonlinear functions, here we'll look at fmin bound, fmin con, we're going to look at an example with. If we have nonlinear least squares, these are suitable functions, such as lsqlin. If we have a multi-objective optimization, here we can use fmin-max. Okay, so we'll find that most optimization solvers, though, do require scalar-valued objective functions. So exemptions of this are fmin-max, which we just mentioned has a multi-value function. It must also take the optimization variables x as input. And your function handle must return the value of the objective function f of x. It may also return the gradient of f and the Hessian of x. If we want to use the user-supplied gradient and Hessian, we need to set the following options to our option struct and pass them in. So here you'll see we'll be turning the gradient to be on and the Hessian to be on as well. If we have vector-valued objective functions, here you'll see that instead of the gradient, we will return the Jacobian matrix. So now let's look at the nonlinear constraints in more detail. Here you'll see that we have c of x is less than or equal to 0 and c of x is equal to 0 for our equality constraint. So how can we do this? If we don't want to specify their derivatives, we're going to have a function handle called constraint function that returns c, which is our inequality nonlinear constraints, as well as our equality linear constraints. If we do want to specify the gradients, you'll see that we'll also return grad c and grad c equality for the inequality nonlinear constraints. Now this is very important. The derivatives must be in the form of gradients rather than Jacobians. We saw that we were using the Jacobian matrix prior. However, for the nonlinear constraints, we are defining the gradient to be the transpose of the Jacobian, as we saw in the first section video. So here it's going to be dcj dxi, meaning that in row 1, it's going to be all of the x1 derivatives of the corresponding constraint functions. And similar syntax for the equality nonlinear constraints. So now let's look at the following exercise. We want to look at the nonlinear constraint optimization problem. So see the nonlinear constraints are popping up here in this circle constraint. We're trying to minimize this objective function subject to the following constraints. So what I'd like you to do would be derive the derivative information for the objective and nonlinear constraints. And you must also convert the optimization problem into MATLAB compatible form, which means that we need the linear inequality constraints in the following form as well as our nonlinear inequality constraints, less than or equal to 0. We're going to solve this using fmin-con. So you'll find the starter code files to do this here. We have fmin-con example. Your code is going to be inputted here. So here we're going to say compute the linearly inequality constraints and also the bounding box constraints. Now we want to turn the grad constraint and grad objective option to be on, and then call fmin star to compute x star and f star. And the rest is just to plot the figures given in the lecture slides. Okay, so I've also broken this up into functions because remember it's very good to subdivide your code into various functions. So here we'll see fmin objective example. So here's where you're going to compute your objective function as well as its gradient. We have an analogous function for the constraint. So you're going to be returning the gradient of the constraint for inequality and also the gradient for the nonlinear equality constraints. So take your time to fill out these code files, and then we will resume. Welcome back. Let's go over the corresponding solutions. So here you'll find fmin-con solution file. Here I've defined the initial guess. I've also had to put ax equals b, ax less than or equal to b, into the MATLAB compatible form. So you'll see I had to take this first constraint and write it on the other right-hand side of the equation. So here a is going to be defined by -1 and -5 since we only have one linear inequality constraint. Our right-hand side is just specified by 0. Our bounding box constraints are given by -2 in each dimension and 2 for the upper bound. Now let's turn on that we want to specify the gradients. To do so, I'm going to set the options on in my option struct. So here you'll see that I've specified them to be off, and I'm also going to specify that we display the iteration. We're going to compare the function count for when they're off to when they're turned to be on. Now we can simply call fmin-con. We're going to supply our objective function handle, our initial guess, the linear inequality constraints. Since we have no equality constraints, we're setting them to be the empty set. These are our bounding box constraints, as well as the function handle to our constraint function and passing in the options struct. So now let's look at the objective file here. So you see that I've defined the objective function f, and I've also defined its corresponding gradient, given right here. But remember, to use it, we need to set the options to be on. For the constraint function, you'll see that we have no nonlinear equality constraints, so we set that to be empty as well as its derivative. Here is our one nonlinear inequality constraint, and we must also specify its derivative given as such. Recall that we want the gradient vector rather than Jacobian, so this is why I'm taking the transpose operation here. So let's look at what output we get from this function. So see the iteration account occurring at each iteration. And here we have the corresponding pictures detailed from the lecture slides. So we'll see that the function count is given by 15 iterations, and we'll see that we converge to this minimum function value, and we've satisfied the constraint. So displaying the iteration can be very helpful because you'll see the maximum constraint violation, your function value to make sure that you're decreasing, also the line search step length, so this is your alpha value. Taking it to 1 is the maximum size, and this will give quadratic convergence for Newton's method. This will also check if you've satisfied the first order optimality condition, meaning that the gradient is close to 0. And this will tell us how often the Hessian has been modified. Now let's say that we do want to pass in our user-supplied gradient information. So here what I'm going to do is go back to the struct. Okay, and now I'm going to say I want to turn them both to be on, and let's see how the output compares. You'll see that now this is much faster, and I've only done 9 function counts in 4 iterations. So it can help to supply the user gradient as well as Hessian operations. So these are the plots that we've given. Here you'll see I'm plotting our objective function, which we're trying to minimize, and this is our constraint set here. So we can visualize the solution as given by these points here. You'll see that it has to live within the constraint. The unconstrained value would be here, but since we have the constraint set, it's given by the pink solution vector. All right, so what about if we want to use the optimization toolbox's GUI? So this will be a very interactive, user-friendly format, in which case we would want to use the problem struct as input as well as options from the workspace. This can generate code for us as well as export the optimization problem to a workspace. So this is again showing the power of MATLAB and its scripting capabilities. So let's take a look at this. Okay, so you'll see here that I can just call OptimTool, and this will open a nice GUI interactive format for me to solve my optimization problem with. So you'll see that you can specify the solver here. So we see fmin_con, and it's defined it for us as constrained nonlinear minimization. So this is a nice summary table. They'll tell us the binary integer programming, fmin search, and also specify what type of optimization problem it solves. So we'll see linprog does linear programming. We can specify our equality constraints, linear inequality constraints, as well as our bounds. We can also specify if we want to use the derivatives, type in our objective function, specify the option struct interactively by using the default tolerance of 1e to the -2 or specifying our own. So this can be very useful to fine-grain the criteria for your optimization. So I recommend using this as well. Lastly, let's do a review of large-scale versus medium-scale optimization. So this is going to be very similar to what we saw in the linear algebra section of whether we want to use full or sparse matrices. So for large-scale optimization algorithm, we're going to be using very large matrices. So the linear algebra, we do not want to store or operate on full matrices. They may be so large that they won't even fit into memory. So here's where we'll want to use sparse matrices and sparse linear algebra. So the internal algorithms, it's important that they preserve the sparsity or do not generate matrices. And this may be used for small problems as well. This is the default option as set by MATLAB. Now, if we want medium-scale optimization algorithms, this will be done on full-scale matrices and dense linear algebra. So an example of this would be the active set method, is a such medium-scale optimization algorithm, which checks which constraints are active. The large-scale algorithm would be interior point. Now, medium-scale optimization algorithms may require significant amount of memory and CPU time for large problems. As a review of which algorithm to choose, you can click on the following link for a nice summary table, depending on your optimization problem. Lastly, which is also very important, we're going to talk about parallel computing and the optimization toolbox. We will talk more about parallel computing when we talk about its toolbox in the later section. For the following MATLAB functions, such as fmincon, fminattain, and fminimax, we can open a MATLAB pool of workers. So these will work concurrently, parallel in memory, so you can speed up the computation. The way to do this is we just need to set the use parallel option to always, and it will turn on par 4. What does par 4 do? It loops over multiple initial conditions. The attempt to find an attempt at global optimization. We'll see this more later, but this is embarrassingly parallel. So your loops have to have a specific structure such that a variable isn't depending on its prior variable in a vector. But for simple loops, such as multiple initial conditions, it can run concurrently. The way that you do this is using the following code syntax. So we're going to open a MATLAB pool of 2 processors, and we're going to set in our option struct use parallel to always. So it doesn't hurt to turn this on, and I recommend it always turning it on just in case that you're able to use this within the optimization toolbox. We've seen that we need to pass in the optimization variable x to our objective function and constraint function, and we've been doing that via function handles. However, what if we need to pass in additional arguments, more than just x? There's ways around this. We can store the variables in anonymous functions, such as function handles. We can also use nested functions. Recall that there's variables sharing between parents and childs. Or we could use global variables for this, if it's necessary for more parameters to be passed in. Again, I don't really recommend using global variables unless you're being very careful. So hopefully this has shown you the vast applications and use of the optimization toolbox, as well as provided you a review of solving nonlinear equations, which is at the heart of numerical optimization, as well as linear algebra.